Everyone. Today's day 3, lesson 3. We're gonna do a really simple thing, actually. Another almost trivial thing similar to the dot product. Very simple, very straightforward. Um, Essentially, we're just gonna do the Euclidean norm, or also known as the L2 norm. Um, we spoke about it for a moment in the lesson 1 video because it's part of the AI generated coding exercise that I wanted to that I didn't actually do in that video, and in real life as well. When I was doing it myself, I just completely blanked on doing the Euclidean norm, so I had done it like thoroughly separately, and it was obviously the easiest thing to do. Um, if you guys have been following along, which I mean, at the time of making this video, I don't think anyone has viewed my videos, but that's okay. Um, Lesson 1, sorry, not lesson 1. In the previous video, I had stated that I had actually had my tabs organized while I was doing this particular exercise, so I can actually walk you through the rabbit hole I went through. So I'm actually gonna do that first and then do the code because the code is very trivial, very easy, very quick. So let's get into it, right? So this was the tab group. I managed to save it, right? What was the first thing I Googled? Obviously, Euclidean norm of vector. How do you do it? And it's just the square root of the elements of the vector squared, right? And squared and summed. Um, Pretty straightforward, pretty simple. And I actually knew this already, but for some reason, when I actually looked this up and I saw this, I'm like, wait, isn't that? And I actually saw this image as well. I'm like, wait, isn't that just Pythagoras theorem, right? Because I remember that, and I don't know why I never made that connection myself because I came I became a data scientist in that like Andrew Ng era, like don't worry about the math kind of era, and I just kind of like learned a lot back then, but I just never made that connection. I'm like, wait, I know this, right? So I just looked up the whether or not it is derived from the Pythagorean theorem, and it is. And actually, I'm just gonna show you something from the first page. When I scroll down, there was this proof that the Euclidean norm is indeed a norm, at which point I was like, wait, what? What do you mean by is it a norm? Right? So, and I just reread the AI generated thing, and I'm like, it's a measure of its length or magnitude. I'm like, okay, that makes sense, but what do you mean by is it a norm? So I had opened up that tab, and this is just a lookup of the Pythagorean theorem. And this is a tab for looking how to do square roots. I know there was like multiple ways, but I just want to like look at it with my own two eyes. Um, I ended up just using the exponentiation to 0.5. But I wanted to go over this one. And this was like, oh, wait, I never actually knew about the properties that define an actual norm, right? So positivity, homogeneity, and subadditivity. Subadditivity. I think that's correct. I'm not sure if I think that's correct. That sounds about right. And I was just reading this and I'm like, wait, what is this? What is this? And like I spent some time just trying to read these three. So it's like the norm of x is greater than or equal to 0 for all x that is subset of x, and x, the norm of x, 0 if and only if x is 0. Okay, positivity. So basically the norm should always be positive, or 0, and it's only 0 if the vector is 0. Homogeneity, basically that if multiplied by a scalar, it's equivalent to multiplying with the absolute value of that scalar. And subadditivity, that the sum of the norm of the sums is less than or equal to the sum of each individual norm. So I think this comes from the triangle inequality, which I ended up exploring. But before I did that, I was just like, what is a norm of vectors? Because I'm like, what are the key properties? And trying to understand that. See, this is where I was saying the triangle inequality. It's essentially an extension of the fact that any side is less than or equal to the length of the other two sides, and it's that same extension with subadditivity, which is the triangle inequality, right? Um, and I looked this up and I was like quite curious. So I kind of kept going with this, looked up the triangle inequality again. It was fairly straightforward. Um, and then I was like really curious as to historically how we went from the Pythagorean theorem to the Euclidean norm, because Pythagorean was obviously just two dimensional, whereas the Euclidean norm is obviously generalizable to n dimensions, right? And I went through this thing and I was like, Cartesian coordinates? Isn't that just like your regular two-dimensional XY plane, which is what I've always called it, the two-dimensional plane? Um, and the once the concept of Cartesian coordinates, which I didn't know was actually created by Rene Descartes. I've heard of Descartes' name in so many random philosophy videos that I viewed while falling asleep. I didn't know that that's actually he was the same guy who came up with Cartesian coordinates, which is probably dumb, but whatever. Um, and I was reading about how the generalization came to multiple dimensions, considering the differences as the legs of a left and right triangle, right? Because that's where Cartesian coordinates came in. It's like, okay, you can do that with any point on the Cartesian coordinate system if you just look at it as a triangle, right? Or as a right angle triangle. Um, and there isn't very good conversation about how we went properly from that generalization in two dimensions in Cartesian space to n dimensions, but I presumed there was a proof of that somewhere, though I don't think I actually looked it up. But what I did look up what other types of coordinate systems there are, and I'm like polar, cylindrical, spherical. I'm like, oh wait, yeah, I remember all of these actually, and I'm just like, coordinate systems just kind of fell into it. So it's just reinforcing that same thing I've discussed a couple of times of, you know, stepping out of your bounds. Don't just learn what you are trying to learn, but learn a little bit more. Just be curious, engage in that curiosity. Obviously you're trying to do it in that, like, do something first and make that doing something aspect tied to how you would actually end up using the thing. So though obviously that line of thinking doesn't work really well when you're trying to learn something just for your own edification instead of for work or to get better in a particular field because that's your career or whatever. But still, it works to some extent, right? um, and then just looked up how do you describe a vector in Cartesian space very specifically, understanding the different components and all of that. And going from there, I was like, wait, okay, so if I can just have all these components be, all the different components, like are originating from zero, then you can describe any vector, right? Because the reason I looked this up is like, okay, what if I'm looking at the distance of 2 points that are not related, right? And that are not like starting at the origin, right? Which is what I was confused by and why I was looking this up, right? And why the next Google is like, do vectors always originate at zero? Which they don't. But what I realized, not even necessarily from looking at this Google, I just came back to this. I'm just looking at it and thinking about it. It's like, okay, just because like I'm looking at a vector that's not originating from zero doesn't mean I can't express it as the sum of vectors originating from zero, right? And the reason I was thinking about this is because it's like when I'm looking at a line in, let's say, two-dimensional space, right? I don't just take the square of the sum of the x and y coordinates, right? I actually have to take the difference of the x and y coordinates first before I do that, right? To actually get the magnitude of that vector that is not originating from zero. If it's originating from zero, you can just like do that, right? And so that's like where that realization came, is like, okay, if this Euclidean norm is happening in n-dimensional space and I'm always I'm expecting in general that in that case it's either a vector that is originating from zero or that can be expressed as originating from zero, right? And so that started to make sense. I'm like, oh, okay. So I didn't really go down this route for that much longer. Ended up looking the exponentiation operator because I thought it was the caret operator, which is my next Google. So I just looked this up and then I went to the next Google, which is like the caret operator. And I'm like, oh, the caret operator is actually the bitwise XOR, the exclusive OR operator. I'm like, oh, okay. I didn't know that actually. And then okay, I don't understand why I looked up the dot product again. There was something here. I don't know why. Oh yeah, and then I looked up how to get like the Euclidean norm from NP-linalg because, well, no, I was just looking up NP-linalg Euclidean norm just to try and figure that out, because I wanted to test my function. And then I ended up going to the NumPy documentation for Linalg norm. I was a little bit confused by this ORD thing because that's apparently the order of the norm, which was like, I'm like, wait, what? I was a little bit confused for a moment. And then I went through these. I'm like, wait, how do I get this? Do I just put ORD 2? Like, that made the sense to me. Like, the 2 norm is, I'm guessing, like the order of the Euclidean norm because you're squaring it, so the order would be 2. Is that right? And I just like ended up Googling what is the order of a norm, and that's when I realized like, oh, the L1 and L2 norms aren't the only norms, right? Like, it's actually there's LP norms, right? And L1, L2 derive from that, and that you can have like an infinite number of this, which was like, what? That like blew my mind. And why do greater than two LP norms? The first was what's so special about P equals 2 for the LP spaces. I didn't go into that really. I started going into the LP space thing. And at this point, this is usually where most rabbit holes will end. You'll start hitting things, but I'm like, okay, I don't know these terms. I'm not understanding 1000% what it's saying. You start hitting bedrock basically of your rabbit hole, and that's okay. You can keep exploring that bedrock like a little bit, trying to understand it, which I did, and I came to this Reddit post, and this does not make a huge amount of sense to me, to be honest. A locally integrable function or a sequence may fail to converge and be in Lebesgue space, blah blah blah. I was a bit lost, so I just like, okay, let's regroup, and I'm going to come to this in a moment. Explain this assert ABS. I actually talked about this in lesson 1 about the asserts and tolerances and floating point precisions, and that's what I was actually figuring out here because when I asked ChatGPT to generate me some test cases, it was using, I knew what assert was, but I wasn't sure why I was doing this and the less than 1e neg 6, and like that's what I was like Googling this over, or just ChatGPTing it in this case. This is just like our test cases. We'll go over that in a moment. Now, in one of the test cases, there was the 5, 12, 13 triangle, right? And it was marked as a special case, like these two. And I was like, huh? Why is 5, 12, 13 special, right? I asked it to write out all the asserts, and I asked it to highlight it. The 0.6.8 it said was the unit vector, which I understood. I'm like, oh, okay, that makes sense. Then what about this? What about y is 5, 12, 13? Introduces a negative component, so okay, that makes sure you're squaring it correctly. It's also well-known 5, 12, 13 triangle, so I'm like, wait, what? What's so well-known about it? And I looked it up. This is just a general thing describing the 5, 12, 13 right angle triangle. I'm like, still, what is special about this? And then I like Google specifically, why is it special? And then I realized it's special because it satisfies a right angle triangle and all the components are integers. I'm like, okay, got it. This is just me looking up more LP space stuff that someday I'll hope to be able to dive deeper into, maybe on this YouTube channel, but it was interesting. And then I was like, I'm trying to hit bedrock here. I should actually go do the thing, which is exactly what I'm going to do. Let's get to the code. It's coding time. Super easy, honestly. It's just like def. Let's go with norm. I'm just going to call it L2 norm. we take a vec, right? What is the Euclidean norm? It's just the magnitude of the vector, which is in this particular case is just the sum of x squared. Oh wait, I used the caret again. Gotta use the exponentiation operator. X squared for x in vec, and then we want the square root of that, so raised to the power 0.5, which is equivalent to a square root. Def L2 norm, do that. I'm just gonna do the I'm just gonna copy my tests from here, placed it here. I'm just gonna run this over. I'm just gonna rename it to Euclidean norm because that's the name I used earlier. Import numpy as np. Numpy as, oh wait, there's an issue with an assert unsupported operating times, non-type and float. Huh? Well, okay, we're gonna code this live. What is the issue? I am confused. Oh, I need to return this. That's why. I'm like, what's going on? And boom, all the asserts passed. No issues there. And we're all working jimmy jammy double fine. Anyways, I'm just gonna talk to you guys for a moment. Like, just be real. Like I said, engender curiosity. That's where it begins. You know, be willing to go down rabbit holes and learn new things. Learn things outside of what you want to learn, because it'll just make it more fun. I think that's the number one thing. I mean, learn by doing, sure. Make that doing somehow related to how you're actually going to use it, sure. These are all positive things, right? You know, try to teach other people. This is what I'm trying to do here. You can actually just pretend to do this. You don't actually have to make the videos. You can just pretend, or you can just grab someone's ear. But you know, people are lonely sometimes, and it's difficult to find someone who wants to hear you yap about math or coding or whatever. My wife definitely doesn't want to, though she is sitting over there and listening to me yap right now as I make this video. She's being very patient. I love her. She's smiling a little bit. We're gonna continue on. Yeah, all of these things add, but you gotta start with that curiosity, that wanting, right? And in this age, it's actually a great starting point because you can indulge in your curiosity at any given time, right? Other tips and tricks, there's like mnemonics, or you know, another thing I recently heard of, which actually makes a lot of sense, is spaced repetition. Like, do it and then come back to it and review it like after a day, then after like 5 days, after like a couple of weeks or whatever. Just like keep checking it out, you know, and that kind of happens automatically, especially if you're working in one direction, because you automatically kind of end up revisiting the previous thing to do the next thing, like I did with dot products and matrix multiplication, obviously, and that's gonna happen again. So obviously by the end of this journey, you're gonna review the earlier parts the most. It really gets harder when you're at the end of that spectrum, right? When you've actually learned a lot of the stuff, it's like, okay, that end stuff is what you're gonna start wanting to review, right? That's and do it like with increasing intervals, you know, do it is spaced up over time, and get good sleep, all kinds of stuff, right? Stopping and thinking, that's a big one that people, I feel like, kind of overlook, because just like read it and just be like, oh, so does that mean like this? Oh, and then like Googling that, you know, kind of like, I mean, like that's what happened with the Euclidean norm, and like how I went down that rabbit hole of like, oh, does this derive from Pythagoras theorem? And you know, actually, I still didn't get a very satisfying answer. That I just kind of fell into another rabbit hole. Anyways, that's the video. Quick one today. Hopefully, it'll be a little bit more stretched tomorrow. Well, not hopefully, but probably, because I think we're going to be doing transposes, probably determinants, inverses of matrices. I might split each one of those into different videos. I'm not sure how exactly I'm going to end up doing that, rather than doing it all in one video. So yeah, hopefully I'll see you guys, all zero of you, as of right now. Peace out. Have a great one.